Welcome all of you. In the last class, we have discussed about the concept curl. Okay, curl curl. After the completion of that curl, your second unit is almost completed. But we are left out with a small topic, that is expressing Maxwell's equations for electromagnetic fields. Okay. Until now, we have discussed Gauss law, Ampere's circuital law, conservative electric field, conservative magnetic field, like that. We have discussed many laws. We need to express those laws in point form as well as in integral form. Okay. So the Maxwell's equations in point form and integral form we need to express. Already we have derived all the equations, just we need to summarize them in a table. That's all. So here in first unit, the basic law that we have discussed is Gauss law. By using Gauss law, electric flux density for complex problems can be easily solved. So the general representation of that Gauss law in point form is given by del dot d bar is equal to rho v, where d is the electric flux density in vector form and rho v is the volume charge density. This we have already derived when I am saying about divergence concept. We have already derived this equation. Just I am summarizing them. So the first Gauss law equation is the Maxwell's first equation, that is del dot d bar is equal to rho v, which is the point form. Okay. Now the integral form of Gauss law is already we have derived during the proof of Gauss law, that is q equal to surface integral of d bar dot ds bar, or that is also equal to integral rho v dv. All these expressions we have derived in our previous classes, just we are summarizing them. Next, we have discussed about conservative electric field. That means conservation of electric field. In this concept, we said that the electric field for a closed surface is equal to 0. That means del cross E bar is equal to 0. We have already defined what is meant by conservative field in our previous classes, which says that del cross E bar is equal to 0, or for a closed path the potential difference is equal to 0. That means it can be expressed in integral form as integral E bar dot dl bar is equal to 0. Okay, this is the conservation of electric field formula. And after that, the third one is Ampere's circuital law. Ampere's circuital law, which states that generally the integral form of Ampere's circuital law is, how we can define Ampere's circuital law? The line integral of magnetic field intensity h bar around a closed path. That means integral h bar dot dl bar is equal to the current that is flowing in that path. Is equal to the current that is flowing in that path, where I can be again written as integral j bar dot ds bar. Integral j bar dot ds bar, where j is the current density and ds is the surface area, differential surface area. Okay, this is the integral form of Ampere's circuital law. Next, how it can be written in point form? Just in our previous lecture, we have discussed about the concept curl. Curl is nothing but cross product. Divergence is the dot product of a vector with del, and curl is the cross product of a vector with del operator. That means here, after derivation in our previous lecture, we have summarized the result, that is del cross h bar is equal to j bar, where this del cross h bar is also called as curl. Okay. Next, conservation of magnetic field. Conservation of magnetic field. So for this, first we need to know some basics. We have already defined what is magnetic flux density B. We have also defined what is magnetic field intensity H, and both these are related as B equal to mu H and for free space mu r is equal to 1, mu equal to mu naught into mu r is equal to 1, so mu naught you can write. Okay, this is the relation between B bar and H bar, and we also know that flux density B equal to phi by A. This is when the flux lines are exactly at right angles to the unit surface area that you are considering. But if at all the flux lines are not perpendicular, are not at right angles with the unit surface area that you are considering, then this flux phi can be written as phi equal to integral B bar dot ds bar. Okay, when you will use this formula for flux phi equal to B into A now, which implies that B equal to phi by A. So phi is B into A means flux density into area. This is when the flux lines, that means if your unit surface area is like this, flux lines should be always at right angles or perpendicular to this surface. But when these flux lines are not perpendicular, if they are crossing at an angle like this, if your unit area is like this, if the flux lines are crossing at an angle instead of right angle, some other angle if they are crossing the unit area, then your flux can be written as phi equal to closed integral of B bar dot ds bar. Okay, if at all you are considering a closed surface, that means if you take a single monopole for that closed surface, similarly as we have stated in electrostatics, what is meant by conservative field? The potential difference for a closed surface is equal to 0. Similarly here also, for a closed surface, we can say that this flux phi is equal to integral B bar dot ds bar is equal to 0. For a closed surface, we can express like this. For a closed surface, phi equal to integral B bar dot ds bar is equal to 0. So, for a conservative magnetic field, what you can write? For a conservative magnetic field, we can write integral B bar dot ds bar is equal to 0. For a conservative magnetic field, integral B bar dot ds bar is equal to 0 in integral form. Now, if you apply divergence theorem for this B bar concept, what does divergence theorem states? The divergence theorem states that a surface integral of a vector quantity can be converted to volume integral through this formula. Surface integral of B bar dot ds bar is equal to volume integral of del dot B bar dv. This is the equation format for divergence theorem. So from this what we can say, del dot B bar is equal to 0. Okay, for a closed surface, the total magnetic flux is equal to 0, which states that integral B bar dot ds bar is equal to 0. Hence we can write this conservation of magnetic field in integral form as integral B bar dot ds bar is equal to 0, and in point form as this del dot B bar is equal to 0. Okay, this is obtained from divergence theorem. So these are the Maxwell's equations both for electric field as well as magnetic field. That means electromagnetic fields, Maxwell's equations, both in point form as well as in integral form. Okay, these equations are very important. You should remember them throughout your electrical career. Okay, so after these expressions, let us solve a small problem based on these expressions. So once again revise these Maxwell's equation. What is the Gauss law in point form? That is the first Maxwell equation, del dot D bar equal to rho v. In integral form, Q equal to surface integral of D bar dot ds bar, or that is equal to volume integral of rho v dv. Next, what is conservation of electric field equation? Del cross E bar is equal to 0. That means for a closed surface, your potential difference is equal to 0. And similarly, integral E bar dot dl bar is equal to 0. This we have already defined during conservative field definition. Next, Ampere circuital law in point form is just curl equation. Del cross H bar is equal to Z bar. And in integral form, from the definition we can write line integral of H bar dot dl bar is equal to the enclosed current, which can be equated to integral J bar dot ds bar, where J is the current density of the surface that you are considering. Next, for conservation of magnetic field, that means for a closed surface, we know that phi is equal to 0. That means integral B bar dot ds bar is equal to 0. That is in integral form. And if we apply divergence theorem for this concept, then we can say that del dot B bar is equal to 0. And this is the expression for flux when your flux lines are not at right angles when passing through the unit area. Okay? These Maxwell's equations are very important. Next, let us deal a small problem based on these expressions. Flux. Find the flux passing through a. Find the flux passing through a plane. At. Find the flux passing through a plane at phi equal to pi by 4 radians. That means your plane is at an angle of pi by 4 means 45 degrees from the reference. When the limits are r is varying from 0.01 to 0.02 and z is varying from 0 to 2. Okay, these are the limits. A current filament of 2.5 amps. A current filament of 2.5 amps is kept on z-axis. A current filament of 2.5 amps is kept on z-axis. That means just the solution is very simple. Here we are considering a straight current carrying conductor which is kept on z-axis. They have said that a current filament of 2.5 amps is kept on z-axis. So this is your current filament which carries a current of 2.5 amps. And what is the height? That z equal to, it is varying from 0 to 2. So 2 meters. At a 2 meters height, you are considering from origin to 2 meters, you are considering the current element. Now, you should consider a plane, because in cylindrical system, any point P is an intersection of a cylinder of radius r and a plane which is making an angle phi with the reference axis, and a plane z which is at a height of z from the origin. Those three surfaces will intersect and give a point P, R, phi, Z in the case of cylindrical system. Now, this is the plane that we have to consider. This is the plane that we have to consider. This plane is making an angle of pi by 4 radians or 45 degrees from the reference. Okay, this plane is making an angle of pi by 4 radians or 45 degrees with the reference. Now they are asking you to calculate the flux that is passing through this plane due to the current that is flowing in this current element. Okay, here in this current element some current is flowing. Wherever there is electric field, there will be magnetic field also. So when your current is flowing like this, according to the right hand thumb rule, flux lines will be passing around this conductor. Flux lines will be passing around this conductor. So while passing, some amount of flux will be passing through this plane also. And they are asking how much amount of flux is passing through this plane. Okay, how much amount of flux is passing through this plane? That flux phi they are asking. Flux. Okay. Next, what is the unit vector perpendicular to this A phi? Unit vector perpendicular to this plane is A phi. Next, they are asking you to find the flux. Flux phi is given by integral of B bar dot ds bar. For a cylindrical system, when you are looking in phi direction, ds bar is equal to dr dz A phi. This you can refer from your coordinate systems. Okay. So B bar is also given as mu naught into H bar, where mu r can be taken as 1 as if we are considering free space. Okay, and what is H bar now? Why we need to calculate H bar means you should substitute that here. Why we need to calculate B bar means to find the flux we need B bar, and ds bar is here. Now H bar, due to a straight current carrying conductor along z axis, we have already derived an expression by using Biot-Savart's law as well as Ampere's circuitous law. What is H bar at a point due to the straight current carrying conductor, infinite conductor placed on z axis? That formula is I by 2 pi r into a phi bar. We already did that, amperes per meter. Now H bar is written as, what is the current that they have given? 2.5 by, leave that r like that. Actually they gave the limits for r. At the ending after integration you can substitute those limits. Leave that r like that, a phi, and 2.5 by 2 pi will give you 0.3978 by r into a phi. Okay, 0.3978 by r into a phi. Now we can substitute that H bar here, B bar. So from this, what is B bar? B bar equal to mu naught into H bar. That means mu naught is 4 pi into 10 power minus 7. 4 pi into 10 power minus 7 into what is H bar? 0.3978 by r into a phi. This is the unit vector. Now after simplifying your B bar is obtained as 5.5 into 10 power minus 7. 5 into 10 power minus 7 by r into a phi. Okay. After simplifying this expression, you are getting B bar as 5 into 10 power minus 7 by r into a phi. Okay. Now substitute this B bar and ds bar in the equation phi. Now your phi is equal to integral B bar dot ds bar. What is B bar? B bar is 5 into 10 power minus 7 by r. 10 power minus 7 by r into a phi dot what is ds bar? Ds bar is dr dz a phi bar. Okay, a phi dot a phi is equal to 1. A phi dot a phi is equal to 1. So you are having integral 1 by r dr, that is equal to, you are having integral 1 by r dr which is equal to log r which is varying from, r is varying from 0.01 to 0.02. Okay, and what is integral dz? That is simply z. Z is varying from 0 to 2. Now after substituting these limits and finding the values, your final value of flux phi is equal to, your final value of flux phi is 1.6 microwebers. Okay, 1.6 microwebers. So phi is integral B bar dot ds bar. B bar we have already simplified, that is 5 into 10 power minus 7 by r into a phi bar. And ds bar in cylindrical system, when looking from phi side, is dr dz a phi bar. So dot product of these two, you take them, a phi dot a phi is equal to 1, and after that integral 1 by r dr means log r, and integral 1 dz means z, and substitute those limits for r and z which are given in the question. So after simplifying, you will get the flux phi value as 1.6 microwebers. Okay, these type of problems may come in your exam. Okay, now let us go for the concepts of scalar magnetic potential and vector magnetic potential. Okay, in our first unit, that is electrostatics, we have defined the electric potential as a scalar quantity. In our first unit, V is some electric potential which we have defined as scalar quantity. If you refer the lectures of work and potential concept in first unit, we have defined there the electric potential V as a scalar. But when you are coming to this second unit magnetostatics, your potential is divided into two potential, that is scalar magnetic potential Vm. First one is scalar magnetic potential Vm, and second one is vector magnetic potential. Vector means it should be denoted with bar on its head, and it is denoted as A bar. Okay, scalar magnetic potential and vector magnetic potential. Here in magnetostatics, that means in second unit, your potentials are divided as, in second unit, scalar magnetic potential Vm and vector magnetic potential A bar. In our first unit, we have derived a relation between electric field intensity E and normal potential difference V as, in our first unit, we have derived that expression as E equal to minus del V. There in electrostatics, we have derived electric field intensity and potential V. Similarly, when you are coming for magnetostatics, E can be compared to H here, because there in electrostatics we are having electric field intensity E bar. In magnetostatics we are having magnetic field intensity H bar. There electric field intensity E bar, and here magnetic field intensity H bar. So H bar is equal to, we can compare the same equation, minus del, here the scalar potential in electrostatics first unit is normal potential V, but here the scalar magnetic potential we have taken it as some Vm. So H equal to minus del Vm. This relation is very important. Similarly, as we have derived E bar equal to minus del V in the first unit, on comparison we are assuming the same quantities in second unit also. There electric field intensity E bar can be compared to magnetic field intensity H bar in second unit. H bar equal to minus del Vm, where Vm is the scalar magnetic potential. Okay, scalar magnetic potential, H bar is equal to minus del Vm. So from the concept of curl, we have already derived that del cross H bar is equal to J bar. This is from the concept of curl we have derived in our previous lecture. So we can substitute del cross in the place of H bar. What we can take? Minus del Vm, that is equal to J bar. That can be written as minus del square Vm equal to J bar. From this only we can express the Laplace equation also. For finding the Laplace equation, we can say that for closed surface, we know that phi equal to integral B bar dot ds bar is equal to 0. Phi equal to integral B bar dot ds bar is equal to 0. And by applying divergence theorem in our previous Maxwell's equation, we have defined that del dot B bar is equal to 0. Where del dot B can be written as mu naught into H bar, that is equal to 0. Where H bar can be taken as minus del Vm. So H bar can be taken as, send that mu naught that side, and del dot minus del Vm is equal to 0, which states that minus can be sent that side. Del square Vm is equal to 0. This is the Laplace equation. Del square Vm is equal to 0. This is the Laplace equation. Del square Vm is equal to 0. Similarly, for electrostatics, the Laplace equation is del square V is equal to 0. For electrostatics, there del square V equal to 0 means V is the normal potential. Here also normal scalar magnetic potential is Vm. So finally we have got the Laplace equation for magnetic fields as del square Vm is equal to 0, where Vm is the scalar magnetic potential. Next, according to the vector operators, we can say that del dot del cross A bar is equal to 0, because the cross product of del with this vector magnetic potential is taken as 0, because in our previous Maxwell's equation we have written that del cross E bar, vector electric field intensity, del cross E bar is taken as 0. So here also del dot del cross A bar can be written as 0. But already from our previous concepts we can say that del dot B bar is equal to 0. Del dot B bar is equal to 0. So on comparison of both these equations, can we write B bar equal to del cross A bar? On comparison of both these equations, we can write B bar equal to del cross A bar by comparing these. Okay. Next, from the curl equation, that means point form of Ampere's circuital law equation, we know that del cross H bar is equal to J bar. This is from the which equation? Point form of Ampere's circuital law. Del cross H bar is equal to 0, where H bar can be written as, because we know that B equal to mu naught into H. B bar equal to mu naught into H. So from this, in the place of H, what we can substitute? B by mu. B bar by mu naught is equal to J bar, which states that del cross B bar is equal to mu naught into J bar. Del cross B bar equal to mu naught into J bar. Okay. So here again we can write del cross, in the place of B bar, what you can write? In the place of B bar you can write del cross A bar. Del cross A bar is equal to mu naught into J bar. Okay, these are just the improvement of equations, that's all. This is nothing new concept. Already we have derived del cross H bar equal to J bar. Already we know these expressions, del dot D bar equal to 0. Just we have assumed some new equation, that is del dot del cross A bar is equal to 0, and on comparison we are improving the equations, that's all. Okay. So after this, del cross A bar, from the previous concepts, this del cross A bar can be written as del into del dot A bar minus del square A bar is equal to mu naught into J bar. So here on comparison we have obtained B bar is del cross A bar, and from the curl equation we already know that del cross H bar is equal to J bar. We know that B equal to mu H, from our childhood we are knowing this. B bar equal to mu naught into H bar. So in the place of H bar, what you can substitute? B bar by mu naught. If you send that mu naught that side, del cross B bar is equal to mu naught into J bar. Okay. So from here, del cross B bar, in the place of B bar, again what you can substitute? Del cross A bar, that is equal to mu naught into J bar. So from our previous formulas in our previous sessions, del cross A bar can be written as del into del dot A bar minus del square A bar is equal to mu naught into J bar. Okay. Here this can be written as, see, I am sending this mu naught that side. Mu naught that side, 1 by mu naught into del cross A bar. In the place of this del cross A bar, this can be written. Just I have improved that J bar equal to 1 by mu naught into del cross A bar means del into del dot A bar minus del square A bar. Now this quantity is made 0 for conservation of magnetic fields. So finally we will be left this current density J bar is equal to 1 by mu naught into minus del square A bar. Okay, that means del square A bar equal to minus mu naught into J bar. This is nothing but Poisson's equation. Okay, so for magnetostatics, what is the Laplace equation? Laplace equation is del square Vm is equal to 0, where Vm is the scalar magnetic potential. And for magnetostatics, the Poisson's equation is del square A bar equal to minus mu naught into J bar. Okay, once compare the Poisson's and Laplace equations for electrostatics and magnetostatics. For electrostatics, we know that the Laplace equation is del square V is equal to 0. In electrostatics, Laplace equation is del square V is equal to 0. This is Laplace equation. Okay, and Poisson's equation is del square V equal to minus rho V by epsilon naught. This is the Poisson's equation in first unit electrostatics. Okay, similarly in second unit magnetostatics, for magnetic fields, the Laplace equation is del square Vm is equal to 0. This is the Laplace equation. And the Poisson's equation is del square A bar equal to minus mu naught into J bar, where A bar is the vector magnetic potential and J bar is the current density of the field that you are considering. Okay, of the surface that you are considering. So these are the Poisson's and Laplace equations for electrostatic fields, and these are the Laplace and Poisson's equations for magnetostatics. Okay, next, this vector magnetic potential A bar can be expressed for different current distributions. What are the different current distributions? Line current distribution, surface current distribution, and volume current distribution. For line current distribution, your vector magnetic field A bar is given as integral mu naught I dl bar by 4 pi r Weber per meter, and your vector magnetic field potential A bar for surface charge distribution. Surface current distribution is integral mu naught K bar ds by 4 pi r Weber per meter, and your vector magnetic potential A bar for volume charge distribution, that is integral mu naught J bar dV by 4 pi r Weber per meter. Okay, here in magnetostatics, vector magnetic potential plays a major role in the distribution of field. Okay, that's why we are expressing those vector magnetic potential for different charge distribution. One is line charge distribution, surface charge distribution, and volume charge distribution. This K bar is the current density for your surface that you are considering. J bar is the current density for the volume charge distribution that you are considering. Okay, so once again I am revising. What are the Poisson's and Laplace equations for electrostatic fields in first unit? In first unit, your Laplace equation is del square V equal to 0, and Poisson's equation is del square V equal to minus rho V by epsilon naught. Okay, this is for first unit electrostatic fields, Laplace and Poisson's equations. And for second unit magnetostatics, what is the Laplace equation? Del square Vm is equal to 0, where Vm is the scalar magnetic potential, and Poisson's equation is del square A bar equal to minus mu naught into J bar, where A bar is the vector magnetic potential. And these are the formulas for vector magnetic potentials for different charge distributions. Okay, so I hope you understood all the scalar magnetic potential equations, vector magnetic potential equations, Poisson's and Laplace equations for magnetostatic fields, and vector magnetic potentials for different current distributions. Okay, so in our second unit magnetostatics, we have covered first introduction to magnetostatics, small definitions and concepts, And after that we have seen Biot-Savart's law. Biot-Savart's law in normal magnitude form as well as in vector form. Biot-Savart's law states that h bar is equal to integral I dl bar cross ar bar by 4 pi r square in vector form. Okay. And applications of Biot-Savart's law includes h bar due to infinite line charge, infinite sheet charge. Okay. And then we are coming for Ampere's circuital law. Ampere's circuital law can be compared with Gauss law in first unit. There where you are applying Gauss law, that surface is Gaussian surface. Here where you are applying Ampere's circuital law, that path is called as Amperian path. Again we have seen the proof for Ampere's circuital law also. Integral h bar dot dl bar is equal to the current that is enclosed. And after that we have seen the applications of Ampere's circuital law. In the applications we have seen h bar due to infinite length of conductor, h bar due to infinite sheet of charge, and h bar in a coaxial cable, 3 derivations. And we have seen one problem, that type of problem may come in your exams. And after that we have seen curl concept which states that del cross h bar is equal to j bar. Okay, after that curl we have seen just in this lecture Maxwell's equations. Maxwell's equations for both electric fields as well as magnetic fields expressed in point form as well as integral form. That we should remember very well. Maxwell's equation. For Gauss law, Maxwell equation is del dot d bar equal to rho v in point form and q equal to integral d bar dot ds bar in integral form. For conservation of electric field, del cross E bar equal to 0 in point form and integral E bar dot dl bar equal to 0 in integral form. Next, for Ampere's circuital law, del cross h bar equal to j bar in point form and integral h bar dot dl bar equal to I, where I equal to integral j bar dot ds bar in integral form. Next, for conservation of magnetic field, del dot b bar equal to 0 in point form and integral b bar dot ds bar is equal to 0 in integral form. Okay, so after those expressions we have also stated that when the flux lines are not perpendicular to the unit surface area, if they are crossing at an angle like this, if your unit surface area is like this and if the flux lines are crossing at an angle instead of 90 degrees, then phi can be expressed as integral b bar dot ds bar, and for a closed surface that is given as 0. And lastly we have defined what is scalar magnetic potential and vector magnetic potential. We have derived some equations, and based on those equations finally we have expressed Laplace equation, where Laplace equation is del square Vm is equal to 0, and Poisson's equations from vector magnetic potential, that is del square A bar equal to minus mu naught into j bar, where A bar is the vector magnetic potential and j bar is the current density of that charge distribution. Okay, and we have also expressed vector magnetic potential for different charge distribution, line charge distribution, surface charge distribution and volume charge distribution. So finally we have completed 2 units. You should get complete grip on first unit as well as second unit, so that our next units will be very easy if you are perfect with these first 2 units. So in first unit we are having basics of vector calculus, coordinate systems which include Cartesian, cylindrical and spherical system, and after that we have seen Coulomb's law in both magnitude normal form and vector form, and Coulomb's law applications, that means E bar, electric field intensity E bar due to infinite line charge, infinite sheet charge and all those derivations. And we have done some problems, and then we are shifting to electric flux density concept, and we have derived a relation d bar equal to epsilon naught into E bar, and after that we have gone to Gauss law definition proof, and after that we have derived the same derivations E bar due to infinite line charge, infinite sheet charge for cable, for shell, for sphere, all those derivations again by using Gauss law. For a given derivation, suppose if you take infinite line charge, E bar due to infinite line charge is rho L by 2 pi r. into rho L by 2 pi epsilon naught r into that unit vector in that direction. Commonly we can take AR bar. Okay. Same derivation if you do with Coulomb's law or with Gauss law, you will get the same formulas. So you should learn the derivations with the help of Coulomb's law, which involve more mathematical simplifications, and we can also derive the same derivation with Gauss law, where the derivation will be very much simplified. So for complex problems, instead of going for Coulomb's law, we can apply Gauss law and we can get the same formula very easily. That is the advantage of Gauss law. And the surface where we are applying the Gauss law is called as Gaussian surface. And d bar should be always perpendicular or tangential to the Gaussian surface that you are considering. Okay. And after that we have seen work and potential concepts, Poisson's and Laplace equations concepts, and divergence concepts. So by that concept, your first unit is completed. And in second unit, we have seen basics of magnetism, Biot-Savart's law in vector form, applications of Biot-Savart's law. Next, Ampere-Circuital law, which is similar to Gauss law. Ampere-Circuital law applications, derivations, and then curl derivation. And after that, we have seen Poisson's and Laplace equations in magnetostatics. And then the last application of magnetostatics is magnetic levitation. There is a particular concept called magnetic levitation. That means in some foreign countries we can observe some trains moving without any wheels. Just it will be running on the balance of the concept of magnetism. That means that magnetic levitation means an object will be held or suspended in space just only due to magnetic force. Okay, how it is held, how it is suspended that much balancedly without any support means only due to the magnetic force that is acting on that object. Okay, suppose here if you are having two poles like this, North Pole and South Pole, and in the middle of that we can hold an object without any support. That concept is called as magnetic levitation, and due to that concept only some trains are running, magnetic levitation trains. Okay, now due to that magnetic levitation concept only that trains are running. That means an object is suspended in space without any support only based on the magnetic force. That magnetic force will balance the gravitational forces and it will hold the object in space without any support. Okay, that is the application of this magnetostatics. Very good application, magnetic levitation trains. Okay, thank you. This is the end of the second unit.